In today's lesson, we're going to revisit probability, and we're going to look at something called a distribution. A probability distribution is a list or a table, that's what we're going to make, of all the different possible outcomes of an experiment. Okay? We're going to start this unit looking at discrete things, and the next unit we'll look at continuous things. So we're connecting statistics to probabilities. Okay? The distribution for a discrete variable, okay, when you make a table, has two columns to it. Okay, column 1 is the different outcomes. Okay, so we'll label those just x. And then px would be the probability of each outcome. The nice thing about a table is because it lists every single possibility, you know it has to come out to 1, the sum. So if I add up this, plus this, plus this, plus this, plus this, it's going to come out to 1. The total probability always makes 100%. So once you've got a few of them, you could actually figure out the last one or you're missing one because you know what's left over. Okay. Once we make a distribution, we could also make a graph or a histogram showing the different likelihood of each event, and different shapes will come up that we maybe have seen before when we looked at statistics, symmetrical shapes or skews or things like that. So we're going to look at some situations today that involves these kinds of questions. So the first one, we have an experiment. It's done where 3 coins are tossed. We're going to make a tree diagram and then create a probability distribution to show the number of tails showing. So let's talk about tree diagrams. Haven't done one of those in a while. What are the stages of this problem? Well, I can toss the first coin. Coin number 1 could be a head or tail. My second coin could again be a head or tail. And it doesn't matter what happened first, these are independent events. And my third coin, head or tail. So making this this tree diagram, I've now shown all the different possibilities of 3 coins. For instance, I could have a head, 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 or a head, head, tail, head, tail, head, and so on, so on, so on. Okay, so that's my tree diagram. The distribution will be what are the different possibilities. So x equals number of tails. Just to remind ourselves of what we're looking for here. The probability of that will be the likelihood that happens. So how many tails could we have? We could have no tails, 1 tail, 2 tails, or 3 tails. The probability of no tails means, well, how many different cases is that? There's only one case that has no tails. Okay? Head, head, head. All the rest have tails in there somewhere. So my probability is going to be 1 out of, how many different cases do we have altogether? If we count our leaves at the end, we know there's a total of 8. So 1 out of 8. How about 1 tail? How many paths have just 1 tail involved in them? Well, if I go through, I could say I had a head, head, tail. There's 1 path. There's 2 paths. There's 3 paths. And everything else has at least 2 tails. So that's 3 out of 8. 2 tails, go through and count them. You could probably find them pretty quickly. We have, let's try this one here, head, tail, tail, there's 1 path. Tail, head, tail, there's 2 paths. And tail, tail, head, there's 3 paths. So again, we have 3 out of 8. And 3 tails, well, there's only 1. 1 out of 8. Just to make sure you got them all right, count up how many things you have. There should be 8 altogether. So I've got 1 plus 3 plus 3 plus 1. That makes 8 out of 8. I've got every single combination of heads and tails that could possibly be. And that's my distribution, all the different combinations. Kind of our key idea here. Part B, draw the probability histogram. So what would that look like? Okay, so a histogram has 2 parts to it. It has x, the number of tails. And what are our possibilities? We could have none, or 1, or 2, or 3. And our probability up the side is the likelihood of something happening. Well, the most probability we have is 3/8. But usually for these things, we say this is probability. We say, okay, there's 1, 100%. So a half, a quarter, and 3/4. Okay, let's draw this out. No tails is 1/8, which is half of the first box. If this is a quarter, this would be 1/8. And then we have 3/8, which is right there. And we have 3/8 again. And then we have 1/8. And there's our probability distribution for throwing coins, or tossing coins, 3 of them. How many tails should you expect to get in a single toss? Okay, so if I was to do this experiment, what should I expect to get? So for part C, to show expected values, and we use the symbol EX. This means the expected. Okay, to do it, what should we expect to get? Well, every time I toss the coin, it should be 50-50, right? So in a single toss, I should expect to get half. Now, obviously, I can't get half of a head, or half of a tail for that matter. This is a theoretical value, not a practical one. You're not actually going to toss and get, oh, I got half heads, half tails. But theoretically, you should expect to get a half. Now, in this case, the expected value is pretty easy to calculate, well, the likelihood of tossing a head or a tail. In other situations, it can be a little more complicated. There's more than one different outcome that's possible. For instance, if you roll a dice, there's 6 different outcomes possible. What's the likelihood? What should you expect to get? Well, it's not 1/6. Okay, so we have a little formula we use to actually calculate expected value. Okay, the expected value, as we were just saying, is a predicted average of all possible outcomes. It's a theoretical number. And the way we can find it actually is by taking the value of something and multiplying it by its probability. And doing that for each different outcome. So outcome 2, outcome 3, outcome 4, all the way to the end, however many outcomes there are. Now the number you get isn't a number that can practically happen most of the time. It's a theoretical number. It's what should occur. Okay, so if we think about this dice idea, when I roll a dice, what should I expect to see on that face? Okay, so I'm going to make myself a little distribution. What are the different things that could happen? So x and px, and I could get a 1 on the dice, or a 2, or a 3, or a 4, or a 5, or a 6. Those are all the different things I could get. The likelihood of each are all the same. It's 1/6. So what should I expect to get? My expected value is, well, I could get a 1, and the likelihood of that is 1/6. Or I could get a 2, and that's 1/6. Or a 3, a 4, a 5, or a 6. Those are all the different outcomes that are possible and the likelihood of each of those. And when I do the math for this, if I actually go through and calculate these, this is like saying 1/6 plus 2/6 plus 3/6 plus 4/6. You can use your calculator if you want to, 5, 6, 6, 6. And add them all up. We end up with 3, 6, 10, 15, 21 over 6, or in other words, 3.5. I should expect when I roll the dice to roll a face that has a 3.5 on it. Well, we know that's not practically possible. You may get a 3, make it a 4, but on average, you should expect to get 3.5. And you might ask yourself, why is that useful? Well, let's say you're playing a game, and the game involves rolling a dice. On average, you should expect to move 3.5 spaces every time. So let's say you roll the dice 10 times. Well, on average, you should expect to move 35 spaces. That could be useful. That's how we design games, to see what's going to happen. Okay, let's try another one. The probability distribution of a discrete random variable. I don't know what this is. Am I rolling a dice? Am I spinning something? Am I playing a game? But it's given by this formula. The probability of some value is given by x squared divided by 14, where x can be the numbers 1, 2, and k. I want to create a probability distribution. So what does that look like? Well, what are the different possible outcomes? I could get a 1, I could get a 2, or I could get a k. The likelihood of getting a 1, so if x is 1, then x squared over 14 will be 1 squared over 14, or 1/14. If x is 2, well, we get 2 squared over 14, or in other words, 4/14. And if x is k, well, then that's just k squared over 14. Okay. I want to show that k has to be 3. How can I do that? What do I know about distributions? I know that distributions, that probability, has to add up to 1. So in other words, I know that 1/14 plus 2/14, oh sorry, not 2, 4/14 plus k/14 have to add up to 1. Now that's fractions. Some of us don't like fractions, so let's make 1 into 14/14. So I've got 5/14 plus, oh, it's k squared, sorry, k²14. Well, I can solve this. Okay. I bring the numbers over, okay, and this gives me 9/14, which is k²14. Now I know both these are 14, so I don't really have to worry about that. What I need to solve is the top. So k squared is 9. So in other words, if I square root it, k has to be 3. So I can solve for parts of distributions if I don't have them by knowing something about a distribution. It has to add up to 1. That was the algebraic way. You probably could have just looked at this and figured out, if I add them all together, I come out to 1. All right, part C, find our expected value. So, expected value is the thing that could happen, which is 1, and the likelihood of it, 1/14. A 2 could happen, that was 4/14. And a 3 could happen, and that was k squared, which we know now k squared is 3, so 3 squared is 9/14. So if we do this, we'll get 1/14 plus 18/14 plus 27/14, which comes out to 36/14. Okay, that's just a theoretical number. We don't know what the situation is, but the process applies to anything that involves a distribution. So let's look at one that we play where we're playing a game. Sorry. All right, a random draw lottery has sold $1 million worth of tickets. Each ticket is worth $5. The prizes and their frequencies are shown here. So we're actually going to take a look at this first example first, just to change the order here. So we have James. He's designed a board game. He's did a spinner, 10 equal sectors. So I have an example here. This is a spinner, and this thing goes around. It's only got 4, but for our question, we'll talk about 10. If the spinner stops on an odd number, a player moves forward double that number of squares. But if it's an even number, they move backwards half that number of squares. So we want to find the expected moves per spin. So we need to make ourselves a probability distribution. So what are the things we could do? What spins can we get? And what are their, in this case, values and their probability? So I actually have an extra column here just so I can talk about the value, because what I spin isn't what it's actually worth, right? I spin a 1, that's an odd number, and our odd number says moves forward double. So their value is actually 2. But if I spin a 2, they move an even number, it moves backwards half. So backwards half is I'm going to lose 1, half of 2. Okay, so 3 would be a 6, but 4 would be a -2. And so on, all the way down to our 10. 5, 6, 7, 8, 9, 10. So I move forward double for odds, back half. Forward double, back half. Forward double, back half. Okay, our probability for each of these is even. They're all 1 out of 10. All the way down, okay? So let's find our expected move. What should I expect to happen in this game? So our expected value is, well, the first thing I could roll is a 1, but its value, the thing I actually care about, is it's worth 2. So I'm going to use the value of that spin, and it happens 1/10 of the time. The next one is I move backwards 1/10 of the time. And then I move forward 6, 1/10 of the time. And then backwards. I'm going to do all these ones here, right? 2, 1/10 of the time. And then forward. And then backwards. Next row. Forwards. Backwards. Forwards, the last one of those, and then backwards. Okay, and if I put that all together, I end up with a calculation of 3.5. Okay, so theoretically, they should expect to move forward 3.5 spaces every time. Just like when you roll a dice with 1 to 6 faces on it, you should expect to get 3.5. Okay? If you and a friend were to play, why would the game not be considered fair? Well, depending on who goes first, if you move forward on average 3.5 times, 3.5 spaces every time, the person who goes first should expect to win, because on average, they're moving first. Okay? And if they move 3.5 spaces before you get a chance to move, well, they're going to win every single time. Okay? The rule for games, when we're developing a game, for it to be fair, there's a star for you. A fair game, so one that each person has a chance to win, has an expected value of 0. If it's not 0, it's not fair. If it's a positive value, you should expect to win. If it's a negative value, you should expect to lose. Fair games have a value of 0. Okay, well, look at that last example now. So in this example, we have a lottery which has sold $1 million worth of tickets. Each ticket sold for $5. The prizes and their frequencies are shown in the following table. So first prize is $100,000, there's 2 second prizes of $50,000, and 5 third prizes of $10,000. And we're asked to find a few things out. Number 1, or part A, how many tickets were sold? Well, if we sold $1 million worth of tickets, and each ticket was $5, we can calculate the number of tickets. Take our million and divide out by how much they cost each, and there's 200,000 tickets. Okay? We need that to be able to figure out the probability of winning prizes. The probability of winning first prize is 1 out of the 200,000 possible tickets. Second prize, well, 2 out of the 200,000 in tickets. And third prize, 5 out of the 200,000 tickets. And we need to know what our different possible outcomes are to figure out the likelihood of actually winning something. Okay, part C. What is the expected prize per ticket? So this is what we've been working on today. So our expected value is the value of something times the likelihood that it happens. Well, I could win $100,000, but the likelihood of that happening is only 1 in 200,000. Not a very good chance. Okay, well, I think that says 2 million there. Get rid of a 0. All right, I could win second prize. I could win $50,000, and the likelihood of that's actually a little bit better. It's 2 out of 200,000. Or I could win third prize, $10,000. Have a sort of better chance. Not that 5 out of 200,000 is a really good chance, but it's better than 2 of winning that. So if we do our math here, okay, type in our calculator, you can use your ABC button if you want to. You should come out with $1.25 per ticket. So theoretically, just by buying a ticket, I should expect to win $1.25. Can you win $1.25? No, that's not one of the winning prizes, but theoretically you should expect that. In other words, that's how much this company has to give out on average per ticket, which allows me now to think about part D. What is the expected profit per ticket? So they sell tickets for $5 and each, and they expect to give out $1.25 per ticket each. So our profit will be the difference between those two things. How much is coming in, okay, the $5, minus what's going out, the $1.25 on average per ticket, means that the company is making $3.75 per ticket. Okay, obviously, they're not giving that out or keeping that. This is our theoretical value here, but it allows us to actually plan things like lotteries to figure out how much money we have to give out based on how many things we sell and what we sell them for. If the company wanted to break even, they had to charge $1.25. If they want to make some money, they charge a little bit more, like they did here, $5. Okay, that's it. That's our introduction to probability distribution. So we're going to be making tables and finding expected values today. Here's our homework questions. Give them a try, see what you can do. If you're stuck, come see me.